There's a rhythm to the universe, a silent, invisible pulse that guides every atom, every planet, and every galaxy in perfect synchrony. Think about that for a moment. The stars above you, the ground beneath your feet, even the air you're breathing right now, all of it moves to the beat of cosmic clocks we can't see but can't escape. These aren't the clocks you check on your wrist or your phone. These are the subtle, fundamental timekeepers woven into the very fabric of reality, ticking away since the dawn of time itself. And here's the wild part. Without them, nothing, literally nothing, would exist as we know it. What if I told you that these hidden clocks dictate everything from the spin of electrons to the dance of galaxies? That the universe isn't just a chaotic expanse but a finely tuned symphony, with each note played at just the right moment. It's a thought that borders on the poetic, but it's also cold, hard science. From the quantum realm, where particles flicker in and out of existence, to the vast stretches of space where black holes warp time itself, these clocks are the unseen conductors of reality. And the more we learn about them, the more we realize how little we truly understand. So why does this matter to you? Because these clocks aren't just out there, they're in you. The same forces that keep planets in orbit and stars burning also govern the tiny processes inside your cells, the beating of your heart, even the way you perceive time. Unraveling their secrets doesn't just satisfy curiosity, it rewires how we see ourselves in the grand scheme of things. Today, we're going on a journey, one that starts with the smallest particles and stretches to the edges of the cosmos. We'll uncover how these clocks work, why they're so precise, and what happens when they go haywire. By the end, you'll never look at time or reality the same way again. Buckle up, the universe is about to reveal its most mesmerizing secret. These cosmic timekeepers are far more than abstract concepts. They are the invisible scaffolding that holds reality together. Take atomic clocks, for example. They don't just measure time, they reveal how atoms themselves act as perfect metronomes, with electrons oscillating between energy levels at frequencies so precise they'd only lose 1 second every 100 million years. That level of accuracy isn't just impressive, it's woven into the quantum fabric of matter. But zoom out to the cosmic scale, and you'll find an even grander timekeeper, the rotation of pulsars. These collapsed stars spin with such regularity that their rhythmic flashes of radiation rival the precision of our best atomic clocks, acting as lighthouses for the universe. What's truly fascinating is how these clocks connect the unimaginably small to the incomprehensibly vast. Quantum fluctuations, those tiny, random pops of energy at the subatomic level, might seem unrelated to how galaxies spin. But scientists now suspect these microscopic ticks could influence the large-scale structure of the cosmos. It's as if the universe operates on multiple synchronized time zones, from quarks to quasars, all humming to the same hidden rhythm. Even gravity itself may function as a kind of clock, with massive objects warping the flow of time around them like a pendulum swinging through space-time. This isn't just theoretical, these clocks have practical consequences we're only beginning to understand. The GPS in your phone works because engineers account for how Earth's gravity makes time run slightly slower at ground level compared to satellites in orbit. Without adjusting for these subtle cosmic timekeepers, your navigation would be off by miles within minutes. On a grander scale, the expansion rate of the universe, what astronomers call the Hubble constant, may ultimately come down to understanding how these fundamental clocks interact across different scales. Some researchers even speculate that dark energy, the mysterious force accelerating cosmic expansion, could be linked to an as-yet unknown temporal mechanism ticking beneath the surface of reality. The deeper we look, the more these clocks seem to whisper the same profound truth. Time isn't just something we measure. It's a dynamic woven into existence itself, a symphony where every particle, planet, and galaxy plays its part in perfect time. Atomic clocks are humanity's masterpiece in the art of measuring time, machines so precise they border on the miraculous. At their heart lies a simple yet profound principle: atoms don't guess, they don't drift. A cesium atom, when excited, will oscillate between energy states exactly 9,192,631,770 times per second. Not 9,192,631,769. Not 9,192,631,771. This number is as fixed as the laws of physics themselves, making each atom a perfect metronome of the quantum world. But here's where it gets even more fascinating. These atomic vibrations aren't just consistent, they're immune to the wear and tear that plagues human-made devices. A pendulum clock slows with friction. A quartz watch drifts with temperature, but deep inside an atomic clock's vacuum chamber, shielded from magnetic fields and cooled to near absolute zero, atoms dance to a rhythm untouched by the outside world. It's as if each cesium atom carries a sliver of cosmic time within it, a tiny echo of the universe's own impeccable timing. Yet for all their precision, atomic clocks are still playing catch-up with nature's grand designs. Out in the cosmos, pulsars rapidly spinning neutron stars flash with a regularity that puts our best atomic clocks to shame. Some pulsars rotate hundreds of times per second, beaming radiation across space with a rhythm so steady, their pulses arrive on Earth with less variation than the ticking of an atomic clock over decades. These celestial timekeepers don't need batteries or maintenance. They're wound by the conservation of angular momentum, a fundamental law as old as the universe itself. The connection between atomic clocks and these cosmic timekeepers runs deeper than mere precision. Quantum mechanics suggests that the same principles governing cesium atoms' vibrations might also dictate how spacetime itself unfolds. At the Planck scale, the smallest meaningful unit of measurement, time may actually be quantized, advancing in discrete steps rather than a smooth flow. If true, this would mean the entire universe runs on something resembling an atomic clock's ticking, just operating at scales and frequencies beyond human comprehension. This revelation changes how we view time itself. We used to think of it as a river flowing steadily in one direction. Now we see it more like the individual frames of a film, each moment a distinct quantum state, with reality flickering forward in sync with these hidden rhythms. Your perception of a continuous present, that's your brain stitching together the universe's quantum clock, ticks into a seamless experience. The implications ripple outward, from redefining how we synchronize global communications to potentially unlocking new physics that could explain dark matter or quantum gravity. What atomic clocks ultimately teach us is humility. In our quest to measure time, we've built devices accurate to 1 second in several billion years, only to discover the universe has been running on similar principles all along, with far greater elegance. Every time you check the clock on your phone, remember, it's not just tracking hours and minutes. It's tapping into the same cosmic beat that guides stars, atoms, and perhaps the very fabric of reality. At the heart of every atom, there's a hidden dance, a ceaseless vibration so small we can't see it, yet so precise it keeps our world running. Electrons don't just orbit nuclei, they hum at specific frequencies, jumping between energy levels like a perfectly tuned instrument. These quantum oscillations are nature's tiniest clocks, ticking away with a reliability that makes even the finest Swiss watch look crude by comparison. But what's truly mind-bending isn't just their precision. It's the growing suspicion that these minuscule rhythms might be orchestrated by something far grander. Picture an electron as a pendulum swinging in a cosmic breeze. Its vibrations aren't random, they're dictated by the fundamental constants of the universe. Change the strength of electromagnetism or the mass of a quark by even a hair, and these oscillations would falter, throwing atomic timekeeping into chaos. That's why physicists see them as more than just timekeepers. They're probes into the deepest workings of reality. Some theories suggest these quantum ticks might even be synchronized across vast distances, entangled through mechanisms we don't yet understand, like a network of invisible metronomes all set to the same universal tempo. This idea isn't pure speculation. Experiments with atomic clocks placed just millimeters apart show their ticks can subtly influence one another, as if space itself is whispering a shared rhythm between them. At colder temperatures near absolute zero, atoms begin to sync up in eerie unison, a phenomenon called quantum coherence. It's as if, when stripped of thermal noise, particles remember they're part of a larger cosmic chorus. Could this be a hint that the universe has a preferred frequency, a master clock encoded in the fabric of space-time? The implications ripple outward. If quantum oscillations are indeed tied to something deeper, it could reshape how we understand time itself. Maybe what we perceive as the steady flow of seconds is actually the cumulative effect of countless subatomic clocks, all vibrating in harmony. Or perhaps these tiny timekeepers are sensitive to gravitational waves, their ticks stretching and compressing as ripples in spacetime pass through them. Some bold hypotheses even propose that dark matter, the invisible glue holding galaxies together, might interact with these oscillations, subtly tuning them like a cosmic hand adjusting a dial. What's certain is this: the more we study these quantum clocks, the more they blur the line between the microscopic and the cosmic. They challenge us to rethink not just how we measure time, but what time actually is. Are we merely observers of these rhythms, or are we, like everything else in the universe, built from them? Every heartbeat, every thought, every tick of the clock on your wall, it all traces back to these silent, subatomic pulses. And that realization doesn't just tell us about atoms, it tells us about ourselves. Pulsars are the universe's own precision, timepieces, cosmic lighthouses, flashing with a rhythm so exact it defies human engineering. Born from the violent deaths of massive stars, these neutron stars pack more mass than our sun into a sphere no wider than a city. As they spin, sometimes hundreds of times per second, their intense magnetic fields funnel radiation into narrow beams that sweep across space like a celestial strobe light. What makes them extraordinary isn't just their speed, but their consistency. Take Pulsar J0437 4715, a pulsar whose flashes arrive every 5.75 milliseconds with such reliability that over decades, its timing varies by less than 100 millionth of a second. That's like a stopwatch that wouldn't gain or lose a second in 3 million years. But pulsars don't just keep time, they test the very laws of physics. When two pulsars orbit one another, as in the famous Hulse-Taylor binary system, their gradually decaying orbits provide the most precise confirmation yet of Einstein's prediction that moving masses should radiate gravitational waves. Each millisecond pulsar becomes a laboratory where space-time itself is stretched and squeezed, its pulses arriving a fraction earlier or later as gravitational waves ripple past. Some pulsars, like those in globular clusters, even serve as galactic GPS markers. their predictable flashes helping astronomers triangulate positions across the Milky Way with astonishing accuracy. What's truly tantalizing is the possibility that these cosmic clocks might be interconnected. Recent observations suggest certain pulsars exhibit timing anomalies, tiny, synchronized deviations in their pulses that some theorists speculate could hint at a deeper network. Imagine if pulsars weren't just isolated timekeepers but nodes in a vast gravitational internet, subtly influencing one another across light years. This idea, while controversial, gains traction when you consider that neutron stars are essentially giant atomic nuclei, their cores potentially governed by quantum phenomena that transcend our current understanding. The implications ripple far beyond astronomy. If pulsars are part of a cosmic clock network, they might help unravel mysteries like dark matter's distribution, or even provide a universal time standard for future interstellar navigation. Already, projects like the International Pulsar Timing Array are treating these stellar beacons as arms of a galaxy-sized detector, listening for the faint hum of low-frequency gravitational waves that could reveal merging supermassive black holes. Every pulse is a message not just about the star itself, but about the invisible fabric of reality it's embedded in. Perhaps the most humbling thought is this: long after our most advanced atomic clocks have fallen silent, pulsars will continue their flawless cadence, indifferent to human timekeeping. They are chronometers built by the universe itself, ticking in the darkness long before life arose, and likely long after we're gone. In their unchanging rhythm, we find both a tool for exploration and a reminder of how much remains to be discovered. Black holes are the universe's ultimate time benders, regions where gravity grows so strong that it doesn't just pull on matter, but warps the very flow of time itself. Picture a clock descending toward a black hole's event horizon. To someone watching from a safe distance, its ticks would stretch out, growing slower and slower until time appears to freeze completely at the point of no return. This isn't an illusion or a trick of perception. It's a fundamental feature of reality called time dilation, where gravity's grip literally stretches seconds into what feels like eternity. Einstein's theory of general relativity explains this eerie phenomenon with a startlingly simple idea: the stronger gravity's pull, the more it slows time's passage. Near Earth's surface, where gravity is relatively mild, this effect is too tiny to notice. Your head actually ages slightly faster than your feet because it's farther from the planet's gravitational pull. But near a black hole, the difference becomes impossible to ignore. A single hour for someone near the event horizon could equate to years or even centuries passing elsewhere in the universe. It's as if the black hole presses its thumb on time's hourglass, letting only a trickle of sand through. What makes this more than just a cosmic curiosity is how it ties into the broader network of universal timekeeping. Black holes don't just distort time, they reveal its intimate connection to space and gravity. The same principles that govern atomic clocks and pulsars also dictate time's behavior near these gravitational monsters. In fact, the extreme time dilation near black holes acts like a magnifying glass, letting us see how all cosmic clocks, from quantum vibrations to spinning neutron stars, are ultimately synchronized by the curvature of space-time itself. This has startling implications. If time can stretch like taffy near a black hole, might subtler versions of this effect be humming along unnoticed throughout the cosmos? Some scientists speculate that dark matter's invisible influence could be subtly altering time's flow in ways we're only beginning to detect. Others wonder if the universe's expansion rate, the so-called Hubble constant, might vary slightly in regions of intense gravity, effectively creating time zones on a galactic scale. Even our GPS satellites have to account for Earth's gravity bending time, adjusting their clocks to stay in sync with those on the ground. The deeper mystery lies in what happens at the event horizon itself, where time appears to stop from an outsider's perspective. Does time truly freeze there, or is this just a limitation of our observations? Some theories suggest that from the falling clock's perspective, time continues normally. It's the universe outside that seems to accelerate in a blur. This paradox highlights how time, far from being universal, is deeply personal, shaped by where you are and how you're moving. Ultimately, black holes don't just bend time, they force us to rethink what time actually is. Are cosmic clocks merely measuring time, or are they helping to create it? Could the universe's smooth flow of moments emerge from countless local timekeeping mechanisms, from quantum jitters to galactic rotations, all woven together by gravity's invisible threads? Each time we study these gravitational giants, we're not just exploring space, we're decoding time's deepest secrets, and that changes everything. The universe has a hidden choreographer, one that doesn't just keep time but literally gives substance to reality itself. Meet the Higgs field, an invisible ocean of energy stretching through every corner of existence. Unlike the clocks we've explored so far, this one doesn't tick or flash. Instead, it hums silently, its vibrations determining the very mass of particles. And without mass, atoms would never clump together, stars would never ignite, and time as we know it would lose all meaning. Imagine throwing a ball into a pool. The thicker the water, the slower the ball moves. Now replace the ball with a subatomic particle and the water with the Higgs field. Particles like electrons or quarks aren't born with mass, they acquire it by interacting with this field, as if swimming through cosmic molasses. Some particles, like photons, glide through unaffected. That's why light travels at the universe's speed limit. Others, like the top quark, slog through like they're wading through syrup, emerging hundreds of times heavier. This isn't just physics, it's the reason you have weight, why trees stand tall, and why planets have gravity to begin with. But here's where it gets stranger. The Higgs field isn't static. Quantum fluctuations make it ripple like a disturbed pond, and some theorists propose these oscillations could act as a kind of universal metronome. If the field's vibrations subtly shift over time, they might tweak the masses of particles, altering the strength of gravity, the nuclear forces, even the expansion rate of space itself. It's a radical idea that the constants we consider unchanging might be set by the rhythm of this invisible clock. To test this, scientists turn to the most precise timekeeping experiment in history, the Large Hadron Collider. By smashing protons together at nearly light speed, they recreate conditions last seen a trillionth of a second after the Big Bang, moments when the Higgs field's oscillations were wilder, more primal. Already, there are tantalizing hints. The mass of the Higgs boson, the field's rippled particle, is eerily precise, as if fine-tuned by some deeper mechanism. And if future collisions reveal unexpected patterns in how the boson decays, it could mean the field isn't just a backdrop but an active conductor, its vibrations synchronizing with other cosmic clocks. Think about what that implies. The same field that gives mass to your body might also be quietly orchestrating the universe's expansion, the stability of atoms, even the flow of time. It's a thread connecting quantum jitters to galactic evolution, a reminder that the cosmos doesn't just keep time, it is time woven from forces we're only beginning to hear. Dark matter might be invisible, but that doesn't mean it's silent. Imagine the cosmos as a grand orchestra, with stars and galaxies playing the melodies we can see. But beneath it all, there's a deep, steady bassline, a rhythm so subtle we've only just begun to suspect its existence. This is the potential heartbeat of dark matter, a mysterious substance that outweighs ordinary matter 5 to 1, yet refuses to interact with light or any instrument we've built to detect it. But here's the twist. Some theories suggest dark matter isn't just sitting there. It could be pulsing, oscillating at frequencies so precise they act like a hidden metronome for the universe. Think of it like this. When you pluck a guitar string, it vibrates at a specific frequency, creating a note. Now replace the string with a dark matter particle, and the note with a ripple in the fabric of space-time itself. Certain models propose that these particles might shift between states, like a pendulum swinging between 2 points, emitting gravitational waves as they move. These wouldn't be the violent waves from colliding black holes that LIGO detects. They'd be a faint, universal hum, a background vibration so consistent it could subtly steer stars within galaxies, explaining why they rotate faster than visible matter alone should allow. The evidence for this idea is still indirect but tantalizing. Take galaxy rotation curves. The outer edges of spiral galaxies spin far quicker than Newton's laws predict, as if some unseen hand is propping them up. Traditional dark matter models solve this by imagining a halo of invisible particles surrounding each galaxy. But what if those particles aren't static? If they're oscillating in sync, their collective rhythm could generate tiny gravitational nudges, like a crowd swaying in unison, gently guiding stars along their paths. Some researchers even speculate that this oscillation might explain why dark matter clumps in specific patterns, leaving faint fingerprints in the large-scale structure of the cosmos. Listening for this rhythm isn't as simple as tuning a radio. Without electromagnetic interactions, scientists have to get creative. One approach involves ultra-precise atomic clocks, the same devices we use to define the second placed in deep space. The theory goes that if dark matter's oscillations permeate everything, they might minutely alter the ticks of these clocks as they pass through Earth. Another method watches for anomalies in pulsar timing arrays. If dark matter's hum distorts spacetime, it could cause pulsar flashes to arrive a hair earlier or later in predictable cycles, like a distant drumbeat warping the air around it. The stakes couldn't be higher. If dark matter truly has its own clockwork, it would mean the universe isn't just filled with invisible mass, it's orchestrated by it. This could unify some of cosmology's biggest puzzles, from galaxy formation to the nature of dark energy. More profoundly, it would suggest that timekeeping isn't just a human obsession or a quirk of atoms and stars. It's woven into the fabric of the unseen majority of reality. Every tick of a clock, every vibration of an atom, might just be echoing a rhythm set in motion by the universe's darkest, most enigmatic performer. Dark energy isn't just pushing galaxies apart, it's rewriting the rules of time itself. Picture a clock where every tick stretches longer than the last, where seconds grow as the universe expands. That's the eerie effect dark energy might have on the cosmos, not just stretching space but diluting time's very fabric. Discovered in the late 1990s when astronomers found distant supernova dimmer than expected, this mysterious force now dominates the universe's energy budget, making up nearly 70% of everything that exists. Yet for all its dominance, we still don't know what it is. The strangest clue lies in how dark energy behaves. Unlike gravity, which weakens with distance, dark energy appears to grow stronger as space expands, its influence magnifying over time like a pendulum swinging wider with each pass. Some models suggest this could mean dark energy isn't constant but evolves, its density shifting over cosmic epochs. If true, the universe might not just be expanding but accelerating at a rate that subtly changes, as if governed by a clock with gears we can't see. What does this mean for time? Einstein taught us that space and time are interwoven, so if dark energy stretches space, it must also warp time. Near massive galaxy clusters, gravity slows clocks down, but in the vast voids between galaxies where dark energy reigns, time might actually speed up. This isn't science fiction. Atomic clocks on satellites already account for Earth's gravity altering time's flow. Future experiments could detect dark energy's subtler effects by comparing clocks in deep space with those on Earth. The mind-bending implication: the universe might not share a single timeline. Your watch here on Earth could tick differently from one placed in the emptiness between galactic superclusters. The stakes go beyond curiosity. If dark energy's strength fluctuates, it could determine whether the cosmos ends in a cold, silent fade or a violent rip. In one scenario, dark energy grows so dominant it tears apart galaxies, then stars, then atoms, a big rip where time itself loses meaning. Alternatively, if dark energy weakens, gravity might regain control, collapsing the universe in a big crunch. Or perhaps dark energy balances perfectly, allowing expansion to continue gently forever. Each outcome depends on how this enigmatic force interacts with time's invisible threads. There's a poetic symmetry here. Just as quantum clocks tick in atoms and pulsars flash in space, dark energy might be the universe's grandest timekeeper, one that doesn't count seconds but shapes epochs. Its rhythm could dictate whether the cosmos has a finite lifespan or stretches into eternity. And while we can't yet hear its beat, every distant supernova, every quasar's flicker, even the cosmic microwave background's faint glow might carry echoes of this ultimate clock, ticking toward a future we're only beginning to imagine. Entropy is the universe's silent conductor, the force that ensures time only marches in one direction. Picture a sandcastle on the beach left alone. It crumbles, never spontaneously reassembling. That's entropy in action, the inevitable drift from order to disorder, the reason ice melts in your drink but never refreezes on its own. This isn't just a quirk of nature, it's the rule that shapes everything from dying stars to the thoughts in your brain. And here's the puzzle: why does entropy only increase? The answer might lie in the very first moment of existence, when the Big Bang set the cosmic stage with an unimaginably low entropy state, like winding up a clock spring to its tightest coil. But entropy isn't just chaos, it's creative. Stars shine because of it. When gravity pulls gas together, entropy increases as heat radiates outward, powering nuclear fusion. Your brain thinks because of it. Neurons fire as ions flow from order to disorder, turning chemical gradients into ideas. Even life itself thrives in this gradient, extracting energy from entropy's relentless climb. The twist: while the universe as a whole trends toward disorder, local pockets like Earth can temporarily defy it, building complexity at the cost of greater chaos elsewhere. Your body is one such pocket, a fleeting eddy in entropy's river. The real mystery is why the early universe started with such impeccable order. Some theorists suggest it's a clue to a deeper reality, that our cosmos is just one bubble in a multiverse, where most regions are high entropy voids, and we simply inhabit a rare low entropy fluctuation. Others propose that time's arrow emerges from quantum mechanics, with particles remembering their past states through subtle correlations, the most radical idea. That entropy isn't fundamental at all, but a side effect of how we perceive a universe where time is ultimately illusory. What's certain is this: entropy binds the microscopic to the cosmic. The same principle that explains why your coffee cools also dictates black holes' eventual evaporation. It's the thread connecting the Big Bang's fiery birth to the distant future when all stars fade, a clock whose ticking can't be ignored, only understood. And perhaps that's the most profound lesson. Time's arrow isn't just a feature of the universe. It might be the universe unfolding one irreversible moment at a time. The moment the universe burst into existence, time didn't just start ticking. It flickered into being like the first fragile spark in a vast, empty void. Picture a clock with no hands, no gears, no face, and then suddenly, impossibly, it begins to count. That's the paradox of the Big Bang's first moments. Our intuition tells us time must have always flowed, but physics paints a stranger picture, a singularity where all known laws break down, and the very concept of before dissolves into quantum uncertainty. What could possibly function as a clock in those initial chaotic fractions of a second? The answer might lie in the quantum foam, a seething sea of virtual particles popping in and out of existence. Some theories propose that time itself emerged from these fluctuations, like ripples solidifying into the steady stream we now experience. Imagine a frozen lake beginning to thaw, first with random cracks, then with interconnected channels, until finally water flows in a recognizable direction. The universe's timeline might have formed similarly, with disjointed quantum events gradually sinking into the coherent rhythm we call time. This leads to one of cosmology's most haunting questions. If time began at the Big Bang, does asking what came before even make sense? It's like asking what's north of the North Pole. Some models, like loop quantum gravity, suggest the Big Bang wasn't a true beginning but a rebound, a prior universe collapsing and bouncing into ours, carrying forward a hidden temporal signature. Others propose that time is merely an emergent property, a side effect of deeper quantum entanglements we don't yet understand. Clues might be hiding in the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature variations in this ancient light could encode patterns from the universe's first trillionth of a second, hinting at how time crystallized from chaos. Even more tantalizing are experiments with quantum clocks, devices so precise they can measure time in increments 1 billion times smaller than a second. By pushing these clocks to their limits, scientists hope to detect subtle discontinuities that might reveal time's granular structure, echoes of its fractured origins. The implications are staggering. If time truly emerged from a timeless state, it would mean our entire existence is riding on a rhythm that wasn't always there. The ticking of atomic clocks, the orbits of planets, even your perception of this passing moment, all might be shadows of a deeper, more fundamental reality where time is just one thread in a tapestry we're only beginning to unravel. And that realization doesn't just change how we see the cosmos. It changes how we see ourselves within it. String theory whispers a radical idea that every particle in the universe isn't a point but a tiny, vibrating loop, each oscillation a perfect cosmic metronome. These aren't just any vibrations, they're precise, quantized frequencies, like the notes on a guitar string tuned to the laws of physics itself. An electron might be one harmonic, a quark another, each mass and force in nature determined by how tightly these strings stretch and vibrate. But here's where it gets surreal. These strings don't just dance in the 3 dimensions we know. They thrum through 6 or 7 hidden spatial dimensions, curled so small we'll never perceive them directly. Imagine a clock whose gears exist in a shadow realm, its ticking audible, its mechanics forever out of sight. This isn't just theoretical poetry. If string theory's vibrations act as fundamental clocks, they could solve one of physics' biggest puzzles: why the constants of nature are so exquisitely fine-tuned for life. The strength of gravity, the mass of an electron, these might not be arbitrary numbers but emergent properties of how strings vibrate across dimensions. Some models even suggest these oscillations could synchronize with larger cosmic clocks, like pulsars or atomic vibrations, creating a hierarchy of timekeeping that spans from the quantum foam to galactic superclusters. Testing such ideas isn't easy when the strings themselves are 1 billion times smaller than an atom. But scientists are creative. One approach looks for faint imprints left by extra dimensions in the cosmic microwave background, ancient light that might carry scars from early universe string interactions. Another hunts for deviations in gravity's strength at microscopic scales, where hidden dimensions could slightly warp its pull. The most daring experiments involve particle colliders like the Large Hadron Collider, where high-energy collisions might, for a split second, excite strings into higher harmonics, producing exotic particles that vanish as quickly as they appear. The wildest implication: if strings truly vibrate across extra dimensions, time itself might flow differently there. A second in our three-dimensional world could stretch or compress in higher dimensional space, like a melody played in a cathedral versus a closet. Some theorists speculate this could explain dark energy's acceleration, an effect leaking into our universe from strings vibrating in unseen realms. Others wonder if quantum entanglement's spooky connections might actually be strings vibrating in unison across dimensions, creating correlations that defy classical physics. What's certain is this: string theory's vision of time is as beautiful as it is elusive. It suggests that beneath the chaos of the observable world, there's a layer of perfect mathematical harmony, where every particle, every force, every moment is a note in a multidimensional symphony. We may not yet have the instruments to hear it clearly, but the search for its rhythm could redefine reality itself. Time crystals shatter one of physics' oldest assumptions, that perpetual motion is impossible. Imagine a clock that ticks forever without winding, a pendulum that swings without ever losing energy. That's the essence of these strange quantum structures, where atoms arrange themselves in patterns that repeat not in space but in time. Unlike ordinary crystals like diamonds or snowflakes with their fixed atomic lattices, time crystals have components that oscillate between configurations at set intervals, creating a rhythm that persists even at absolute zero, where all other motion stops. It's as if these structures have tapped into some hidden groove of the universe, dancing to a beat no external force provides. The discovery sent shockwaves through the scientific community when Nobel laureate Frank Wilczek first proposed the idea in 2012. Skeptics dismissed it as violating the laws of thermodynamics. After all, everything from bouncing balls to orbiting planets eventually loses energy to friction or radiation. But by 2017, two separate teams had created time crystals in the lab using chains of ytterbium atoms and nitrogen vacancy centers in diamonds. The key was quantum entanglement, that spooky connection where particles influence each other instantaneously across distances. When entangled particles form a time crystal, their collective behavior locks into a stable oscillation, like a choir sustaining a note through perfect harmony rather than individual breath. What makes time crystals revolutionary isn't just their defiance of classical physics, it's what they reveal about time itself. Normally, physical laws work the same whether time runs forward or backward. But time crystals break this symmetry, establishing an arrow of time even in microscopic systems. Some theorists speculate this could mirror how the early universe transitioned from timeless quantum foam to the structured flow we experience now. Others see potential for ultra-precise quantum clocks far more stable than atomic timekeepers, or as building blocks for error-resistant quantum computers that use these oscillations as reliable memory states. The most tantalizing possibility: time crystals might be more than laboratory curiosities. Certain models suggest similar structures could exist naturally in neutron stars, where extreme pressures and quantum effects might generate self-sustaining temporal patterns. If so, the universe could be threaded with these hidden clocks, their quiet ticks resonating through space-time like vibrations in a cosmic drumhead. Whether human-made or naturally occurring, one thing is clear: time crystals don't just keep time, they challenge our deepest understanding of what time actually is. And that realization blurs the line between science fiction and the next frontier of physics. The cosmic microwave background isn't just ancient light, it's a time capsule from the universe's first breath, carrying whispers of a moment when time itself was still finding its rhythm. Picture this, a faint glow, cooler than the deepest reaches of space, bathing the entire cosmos. It's the afterglow of the Big Bang, stretched over 14 billion years into microwaves, yet still bearing the scars of the universe's fiery birth. Those tiny temperature fluctuations, some regions slightly warmer, others cooler, aren't random. They're the imprint of quantum jitters from when the universe was less than a second old, frozen into the fabric of reality as space-time expanded. Zoom in on these patterns and you'll find something astonishing. The fluctuations aren't chaotic, they follow precise mathematical relationships, like the harmonics of a musical instrument. Cosmologists call this the acoustic peak spectrum, a relic of pressure waves that rippled through the early universe's plasma, compressing and rarefying matter in regular cycles. It's as if the infant cosmos had a heartbeat, a rhythm set by the interplay of gravity and radiation. These peaks and troughs aren't just artifacts, they're the universe's first timekeepers, oscillations that later seeded galaxies, clusters, and the vast cosmic web we see today. But the cosmic microwave background might hold deeper secrets. Some theorists speculate that these temperature variations could encode clues about time's very nature. One provocative idea suggests that the largest scale patterns, those stretching across billions of light years, might reflect quantum fluctuations from an era before time as we know it existed. If true, the microwave background isn't just a snapshot of the early universe, it's a palimpsest, overwritten with hints of a more fundamental reality where time emerged from timelessness. The evidence lies in anomalies, subtle quirks in the data that defy standard models. For instance, the axis of evil, a curious alignment of temperature fluctuations that seems to prefer one direction over others, or the unexpected cold spot in the southern sky. Could these be echoes of pre-Big Bang physics, artifacts of a cosmic clock winding up before time began ticking? Some models of loop quantum gravity or string theory suggest so, proposing that the universe's initial conditions were set by processes transcending our notion of time entirely. To decode these messages, scientists deploy instruments like the Planck satellite, which mapped the microwave background with unprecedented precision. Future observatories, like the proposed CMB-S4 experiment, aim to detect even fainter signatures, perhaps primordial gravitational waves or traces of cosmic strings that could reveal how time crystallized from quantum foam. Every photon in this ancient light is a messenger, carrying news from an epoch when the universe was too young for stars, galaxies, or even atoms, but old enough to have already set the tempo for everything that followed. What's humbling is realizing that this glow isn't just something we observe, it's something we're inside. The cosmic microwave background fills every cubic centimeter of space, including the room around you. Your body is bathed in these microwaves right now, photons that have traveled since the beginning of time to reach you. In a very real sense, we're not just studying the universe's first clock, we're living in its echo. And that connection between the cosmic and the personal is what makes this search more than science. It's a quest to understand where time comes from, and by extension, what it means that we're here to measure it at all. Neutrinos are the universe's most elusive timekeepers, particles so ghostly they pass through entire planets like moonlight through glass. Yet their subtle transformations might hold the key to an unseen cosmic rhythm. Every second, trillions of these phantom particles stream through your body, unnoticed and unfelt, born from the hearts of stars, violent supernova, or even the Big Bang's fading echo. But here's what's mesmerizing: they don't stay the same. A neutrino born as one flavor, electron, muon, or tau, can shape-shift mid-flight, morphing between identities like a dancer cycling through costumes. This metamorphosis, called neutrino oscillation, isn't just random. It follows a precise mathematical cadence, as if each particle carries an invisible metronome dictating when and how it changes. The implications are staggering. For decades, physicists assumed neutrinos were massless, as the standard model of particle physics insisted. But oscillations proved otherwise. These particles must have mass, however slight, to undergo such transformations. That tiny mass disrupts the otherwise flawless symmetry of particle physics, hinting at gaps in our understanding big enough to drive a quantum truck through. Some theories suggest neutrino oscillations could be evidence of extra dimensions, their mass and rhythm influenced by vibrations in hidden folds of spacetime. Others propose that neutrinos interact with an undiscovered field, a cosmic partner to the Higgs, tuning their oscillations like a pendulum swinging through molasses. Detecting this rhythm is a feat of absurd precision. Imagine trying to clock a stopwatch hidden inside an avalanche. That's the challenge of measuring neutrino oscillations. Facilities like Japan's Super Kamiokan, a cavernous tank filled with 50,000 tons of ultra-pure water, wait for the rare moment a neutrino collides with an atom, releasing a faint blue flash called Cherenkov radiation. By comparing the flavors of neutrinos at their origin, like those from the sun or particle accelerators, to those detected miles away, scientists map their rhythmic shifts. The data reveals a bizarre truth. Neutrinos don't just oscillate, they do so differently depending on whether they are passing through matter or the void of space, as if Earth itself is a filter in their cosmic symphony. What's most tantalizing is how these oscillations might sync with other cosmic clocks. Some models speculate that neutrino rhythms could be entangled with dark matter's hidden pulsars or even gravitational waves, their oscillations tweaked by the stretching of spacetime. There's even a wild hypothesis that neutrinos' timekeeping could explain why the universe is made of matter rather than antimatter. Their asymmetrical oscillations in the early cosmos might have tipped the scales toward everything we see today. Neutrinos remind us that time isn't just something we measure, it's woven into the fabric of existence at every scale. From the quantum flutter inside an atom to the slow spin of galaxies, the universe hums with rhythms we're only beginning to hear. And these ghostly particles slipping through our detectors and our planet alike might be carrying the sheet music. Gravitational waves are the universe's way of ringing like a bell, deep, resonant vibrations that echo through the very fabric of space and time. When two black holes spiral toward each other, their immense gravity warps spacetime like hands twisting a sheet of rubber. As they finally collide, merging into a single, more massive object, the shockwaves ripple outward at the speed of light, stretching and squeezing everything in their path. These aren't just random distortions, they carry a precise signature, a chirp that starts slow and low, then rises to a crescendo before fading into silence. That chirp is more than a sound. It's a time-stamped message from the event, encoding the masses of the black holes, their spin rates, even the distance they traveled to reach us. What makes gravitational waves so extraordinary as timekeepers is their purity. Unlike light, which can be scattered or absorbed by dust and gas, these ripples pass through the cosmos almost untouched, carrying information from the universe's most violent events with near-perfect fidelity. The first direct detection in 2015, a signal dubbed GW150914, wasn't just a scientific triumph. It was humanity's first real-time glimpse of a cosmic clock operating on a scale we'd only theorized. The merging black holes, located 1.3 billion light-years away, had completed their dance long before Earth formed, yet their gravitational waves arrived with a precision that would make an atomic clock blush. But here's what's truly mind-bending. Gravitational waves don't just tell us about isolated events. They reveal how space-time itself behaves as a dynamic medium. Each passing wave momentarily alters the distance between objects, including the mirrors in detectors like LIGO and Virgo, by fractions of a proton's width. This means that in theory, every massive object's movement, from orbiting stars to colliding galaxies, leaves a faint imprint on spacetime's structure, like fingerprints on a cosmic clock face. Some researchers speculate that the universe might be filled with a gravitational wave background, a faint, persistent hum from countless mergers across cosmic history, all overlapping into a kind of universal metronome. The implications stretch far beyond astrophysics. If gravitational waves interact with other fundamental timekeepers like quantum oscillations or dark matter's hidden rhythms, they could help solve mysteries like why time appears to flow in one direction. There's even a wild possibility that primordial gravitational waves, generated during the Big Bang's first instance, might carry patterns from a pre-time quantum state, offering clues about how time emerged in the first place. Every new detection adds another piece to the puzzle, another tick in the grand cosmic clock we're only beginning to hear. The holographic principle turns our understanding of time inside out. What if the steady tick of cosmic clocks is just a surface-level illusion, like shadows dancing on a cave wall? Picture this: every event you've ever experienced, every second that's ever passed, might not be fundamental at all. Instead, time could emerge from a deeper, timeless reality, the way a 3D hologram springs from a 2D surface. It's a concept so radical it makes black holes look mundane. Think of the universe as a cosmic movie screen. The images moving across it, galaxies spinning, stars burning, your life unfolding appear to have depth and time, but they're actually projections from a boundary layer where time doesn't exist. In this view, atomic vibrations and pulsar flashes aren't primary phenomena. They're secondary effects, like the ripples on a pond reflecting the wind's invisible touch. Even entropy's relentless march, that arrow of time we thought was absolute, might just be a statistical artifact emerging from timeless quantum entanglement. The math behind this isn't science fiction. It stems from black hole physics, where theorists discovered that all the information swallowed by a black hole could be encoded on its event horizon, a surface, not a volume. Extend that idea to the entire cosmos, and you get the holographic principle. Our 3D universe might live on a 2D boundary at its edge, with time itself emerging from how that boundary's information interacts. Clocks wouldn't measure time's flow. They'd track correlations between quantum states, like counting how often dominoes fall in an endless chain. Here's where it gets spine-tingling. If time is emergent, then the Big Bang wasn't the beginning. It was the moment the hologram booted up, translating timeless quantum data into a narrative we experience as past, present, and future. Cosmic microwave background patterns, just pixels in the projection. Dark energy's acceleration may be a glitch in the rendering. Even your sense of free will could be part of the illusion, your choices predetermined by correlations in the underlying code. Yet for all its strangeness, the holographic principle isn't untestable. Physicists are designing experiments to hunt for evidence of spacetime's pixelated nature, tiny, fundamental bits of reality that might shimmer into view at ultra-small scales. Others are probing quantum computers for signs that entanglement, that spooky connection between particles, might actually be the glue binding the hologram together. If they succeed, we'll confront a truth far stranger than fiction. that time, the scaffold of our existence, is no more real than the motion in a flipbook, a trick of the cosmic light. Quantum entanglement is the universe's most baffling duet, a performance where particles separated by galaxies move in perfect, instantaneous harmony, as if sharing a hidden conductor. Picture two electrons born from the same atom, spinning in opposite directions. Even if you fling one to the edge of the observable universe, measuring its spin will instantly lock its partner into the opposite state, faster than light could bridge the distance between them. Einstein called this spooky action at a distance, a phrase that captures both the phenomenon's eerie nature and how thoroughly it defies classical intuition. What if this spookiness isn't just a quantum quirk, but a clue to something deeper? Entanglement doesn't just link particles, it creates a shared rhythm, a synchronization so precise it could rival the most accurate atomic clocks. Some theories suggest these correlations aren't random but reflect an underlying temporal architecture, a kind of quantum metronome ticking beneath spacetime's surface. Imagine every entangled pair as part of a vast, invisible network, their states flipping in unison not because of signals sent through space, but because they're all attuned to the same fundamental clockwork. The implications stretch far beyond laboratory curiosities. If entanglement does encode a universal timekeeping mechanism, it could rewrite our understanding of causality. Normally, time's arrow demands that cause precedes effect, but entangled particles seem to bypass this rule, their coordinated states implying a reality where before and after lose meaning. This isn't just theoretical. Quantum computers already exploit entanglement to perform calculations, their qubits humming in sync across chips, hinting at a future where timekeeping isn't local but woven into the fabric of information itself. Here's where it gets stranger. Experiments with entangled photons show their synchronization persists even when one particle's measurement is delayed until after its partner has been recorded. It's as if the universe retroactively adjusts their states to maintain harmony, like a composer rewriting a symphony's opening notes after the finale has already played. Some interpretations suggest this means time at the quantum level isn't linear but fluid, with entanglement acting as a bridge across its folds. Could this explain why the cosmos appears so finely tuned? If entanglement networks scale up to galactic proportions, linking particles across stars or even threading through dark matter, they might form a hidden lattice of synchronized timekeepers, subtly guiding the universe's evolution. Black holes, with their extreme gravity, might even sever or twist these threads, creating localized time anomalies. Meanwhile, cutting-edge detectors are hunting for gravitational waves' influence on entangled particles, probing whether spacetime ripples could nudge this quantum clockwork. The most radical idea, entanglement might not just mimic a clock, it could be time's foundation. In certain quantum gravity models, spacetime itself emerges from entangled qubits, with every tick of your wristwatch tracing back to microscopic correlations in the void. That would mean the steady flow of seconds we experience is a collective illusion, a symphony played by countless entangled particles we can't even see. And if that's true, then time isn't something the universe has, it's something the universe is. The multiverse isn't just a collection of alternate realities, it's a symphony of possible times, each universe humming to its own rhythm. Imagine a cosmos where gravity is 10 times stronger. Stars would burn faster, collapsing into black holes before life could even blink into existence. Time itself would feel heavier, dragging seconds like molasses for any hypothetical observer. Now flip it, a universe where gravity is a whisper, so weak that matter barely clumps together. There, cosmic clocks might tick dizzyingly fast, with galaxies forming and evaporating in what we'd call an eye blink. These aren't thought experiments, they're glimpses into how fragile our experience of time really is, balanced on a knife's edge of physical constants. Consider the fine structure constant which governs electromagnetism's strength. In our universe, it's roughly 1/137, a number that ensures atoms hold together just right. But tweak it even slightly and the cosmic orchestra falls out of tune. A larger value might mean electrons orbit nuclei too tightly, preventing chemical bonds. Time in such a universe wouldn't just run differently, it might not even be measurable with no stable atoms to build clocks. Conversely, a weaker constant could stretch atomic vibrations into sluggish, drawn-out pulses, making seconds feel like eternities. Then there's the arrow of time. Our universe insists on entropy increasing, giving time its one-way street. But could other universes have different rules? A cosmos where entropy fluctuates randomly might experience time as a series of loops with causes sometimes following effects. Or picture a universe where the big crunch, a collapse back into a singularity, is inevitable. There, time's arrow might reverse during contraction, with shattered teacups reassembling and memories unraveling backward. The wildest possibility, universes where time isn't fundamental at all. If our perception of time emerges from quantum entanglement or holographic data processing, other realities might encode time in ways we can't begin to fathom. A universe with extra spatial dimensions might treat time as a secondary effect, like shadows cast by higher dimensional vibrations. Another might have multiple time dimensions, with events unfolding along intersecting temporal axes, a reality where now is as malleable as clay. What ties these speculations together is a humbling truth. Our clocks, from atomic vibrations to pulsar flashes, are local instruments. They measure time as it exists here under these laws. But beyond the horizon of our cosmic bubble, if the multiverse is real, time might not just run differently. It could rewrite the very definition of run. And that realization doesn't just expand our view of reality. It makes every tick of your watch feel like a postcard from one very specific corner of an unimaginably vast temporal tapestry. Biological clocks don't just keep time, they might be carrying echoes of the cosmos itself. Deep within your brain, a tiny cluster of cells called the suprachiasmatic nucleus acts as the body's master clock, synchronizing everything from hormone releases to sleep cycles with Earth's 24-hour rotation. But here's the startling part. This rhythm persists even in total darkness, drifting only slightly off the solar day. It's as if our bodies aren't just responding to sunlight, but are tuned to something deeper, a fundamental tempo that predates artificial lighting and modern schedules. Consider the humble fruit fly. When raised in labs under controlled light conditions, generations of these insects still maintain circadian rhythms matching Earth's rotation. But in experiments where gravity is altered, like aboard the International Space Station, their biological clocks go haywire, suggesting gravity itself might be one of the hidden conductors of life's metronome. Similar patterns emerge in humans. Astronauts experience disrupted sleep and hormonal imbalances in microgravity, as if their bodies are searching for a rhythm that no longer matches their environment. The connections grow stranger when you zoom out. Some species, like the bristlecone pine, live for millennia with growth rings that correlate to solar cycles. Others, like the periodical cicada, emerge precisely every 13 or 17 years, prime numbers that coincidentally help them avoid predators synced to shorter cycles. Could these patterns be mere evolutionary accidents, or might they reflect an unconscious synchronization with cosmic timekeepers? Certain studies hint that organisms can sense subtle cues like geomagnetic fluctuations or even cosmic rays, using them to fine-tune biological processes. Perhaps the most provocative evidence comes from human history. Ancient cultures from the Maya to the builders of Stonehenge structured their lives around celestial cycles, developing calendars that tracked not just solar and lunar phases, but longer cosmic rhythms like the precession of equinoxes, a 26,000-year wobble in Earth's axis. Modern research reveals that our cells contain proteins called cryptochromes, which respond to magnetic fields and may link our biochemistry to planetary magnetism. Some scientists speculate these molecules are evolutionary remnants of a time when life relied on cosmic cues we've since forgotten how to consciously perceive. The implications ripple through medicine, space exploration, and our understanding of consciousness itself. If biological clocks are indeed sensitive to cosmic rhythms, it would mean we're not just observers of the universe's timekeeping, we're participants, our very cells vibrating in tune with forces we're only beginning to map. From the sleep you lose during a full moon to the unexplained timing of certain migratory patterns, the cosmos might be whispering to biology in a language we're just now learning to hear. The cosmos hums with countless timekeepers, pulsars, quantum vibrations, even the slow creep of entropy. Yet amid this symphony, one voice remains conspicuously absent, the tick of alien clocks. The Fermi paradox takes on a haunting new dimension when we consider that any civilization advanced enough to harness the universe's rhythms would likely leave temporal fingerprints across the stars. So where are they? One possibility is as unsettling as it is elegant. They've transcended time itself. Imagine a species that's moved beyond physical clocks, encoding their presence in quantum fluctuations or gravitational waves, their signals so finely tuned they blend into the background static of spacetime. To them, our frantic radio broadcasts and atomic timekeeping might seem as primitive as smoke signals. Then there's the chilling alternative. The universe's clocks might be ticking too slowly for civilizations to ever sync up. Consider the timescales involved. Even if 1,000 advanced civilizations arose in our galaxy, their golden ages could be separated by millions of years like fireflies blinking in the dark, never overlapping long enough to spot one another. Pulsar signals that could serve as interstellar lighthouses take millennia to cross the void, and by the time they arrive, the civilization that might have interpreted them could already be dust. Time, in this view, isn't just a medium for communication. It's the ultimate silencer, stretching signals so thin they dissolve into cosmic noise before anyone can listen. But the paradox cuts deeper. What if the absence of alien timekeepers is evidence that intelligence itself is a fleeting anomaly in the universe's grand rhythm? Life might arise only in the narrowest sliver of cosmic history, wedged between epochs too volatile for complex chemistry or too cold for energy-intensive thought. Or perhaps the universe's strictest clock, entropy's irreversible march, dooms all civilizations before they can master interstellar signaling. The same thermodynamics that powers stars and cells also ensures that every ordered system, no matter how clever, eventually succumbs to chaos. Yet there's a third, even more provocative angle. We might be searching for the wrong kind of time. Human clocks measure seconds and years, but an advanced civilization could perceive time in ways we can't fathom, sculpting it like clay in extra dimensions, or treating it as a fluid resource to be shared across entangled particles. Their messages might not be radio pulses or laser beams, but deliberate manipulations of spacetime's fabric, ripples we haven't yet learned to decode. The silence of the cosmos, then, isn't emptiness, it's a library where we've yet to recognize the language of the shelves. The Fermi paradox, viewed through the lens of time, becomes less about distance and more about dissonance. We're listening for an echo in a universe that might be whispering in a frequency beyond clocks altogether. And that realization doesn't just refine the search for extraterrestrial intelligence, it redefines what intelligence might even look like when time itself is the canvas. Time travel might not require a DeLorean or a spinning phone booth, just a deep understanding of the universe's hidden clocks. The idea of bending time isn't pure fantasy. It's woven into the fabric of Einstein's equations, where gravity warps space-time like a heavy ball sinking into a trampoline. Wormholes, those hypothetical shortcuts through the cosmos, could, in theory, connect distant moments as easily as distant places. But here's the catch: the universe's timekeepers might not let us cheat so easily. Every tick of an atomic clock, every pulse of a neutron star, every vibration of the Higgs field could be enforcing cosmic rules we're only beginning to decode. Take closed time-like curves, for example. These are paths through spacetime that loop back on themselves, allowing an object to return to its own past without breaking any physical laws. On paper, they're mathematically sound, but in reality, they'd require conditions so extreme, like the infinite energy of a spinning black hole or exotic matter with negative mass, that they might as well be locked behind a celestial vault. Even if we could engineer such a scenario, quantum mechanics throws another wrench in the works. The slightest interaction, a single photon bouncing off a time traveler, could trigger paradoxes that unravel the very event you are trying to visit. It's as if the universe has built-in error correction, ensuring its clocks stay synchronized and its timeline untangled. Yet there's a tantalizing alternative. Instead of forcing time to bend, what if we learn to ride its natural rhythms? Pulsars flash with such regularity that advanced civilizations might use them as waypoints for navigation across millennia. Quantum entanglement's spooky synchronization hints at a layer of reality where cause and effect aren't strictly linear, where before and after might be more fluid than we think. Even dark energy's accelerating expansion could be a kind of temporal current, carrying the universe toward futures where time's arrow behaves in ways we can't yet predict. The most radical possibility, time travel might already be happening, just not in the way Hollywood imagines. Black holes stretch seconds into eons for distant observers, while atomic clocks on GPS satellites tick faster than those on Earth, proving time's malleability isn't theoretical. If we could harness these effects deliberately, we might not need to build a time machine. We just need to find the right cosmic current and learn to surf it. But until then, the universe's clocks keep ticking, indifferent to our dreams of rewriting history, or at least that's how it appears from our limited vantage point in the here and now. The universe's clocks have been ticking for nearly 14 billion years, but nothing lasts forever, not even time itself. Picture a future so distant that every star has burned out, every black hole has evaporated, and the cosmos is left as a vast, featureless void. This is heat death, the ultimate cold, silent end where entropy reaches maximum and all energy dissipates into equilibrium. In this state, there's no more change, no more motion, just an eternal, unchanging sameness. And without change, time loses all meaning. It's not that clocks stop ticking, it's that there's nothing left to measure. No pulsars flashing, no atoms vibrating, no light or heat or life. Time, in effect, would simply fade into irrelevance, like a metronome still swinging in an empty concert hall long after the music has ended. But heat death isn't the only possible finale. Another scenario, the Big Crunch, flips the script entirely. Imagine gravity eventually overcoming dark energy's expansion, pulling all matter back together in a reverse of the Big Bang. Galaxies would collide, temperatures soar, and space-time itself crumple into a singularity. Here, time wouldn't just stop, it might invert, rewinding the universe's history in a surreal backward cascade. Some theories even suggest the crunch could trigger a new Big Bang, birthing a fresh universe with its own timekeeping rules. In this cyclical model, cosmic clocks don't truly end. They reset, like an hourglass flipped the moment its last grain falls. Then there's vacuum decay, the most unsettling endgame of all. Our universe might be sitting in a false vacuum, a seemingly stable but precarious energy state. If a quantum fluctuation nudges spacetime into a lower energy true vacuum, it could unleash a bubble of destruction expanding at light speed, rewriting the laws of physics as it goes. Within this bubble, time as we know it would cease, replaced by something entirely alien. Atomic clocks, pulsars, even causality could dissolve in an instant, erased by a fundamental rewrite of reality's code. The most profound question isn't just how time ends, but whether end is even the right word. Certain quantum gravity models propose that time isn't fundamental but emergent, like temperature arising from atomic motion. If so, its disappearance might not be an ending at all, just a phased transition into a timeless state where the universe's underlying quantum bits persist, rearranged. Others speculate that consciousness itself might be the anchor for time's flow, meaning that without observers, time loses its grip entirely. These scenarios aren't just scientific speculation, they're mirrors held up to our deepest existential fears and hopes. Whether time halts, loops, or transforms, its potential endings force us to confront what truly makes a universe meaningful. And that's the paradox. By pondering time's demise, we're reaffirming its value in every moment we have left. Could the universe's countless timekeepers, from the frantic vibrations of quarks to the stately spin of galaxies, all be synchronized by some deeper, unseen rhythm? The idea isn't just poetic, it's a scientific frontier that could rewrite our understanding of reality. Picture a cosmic symphony where every instrument, no matter how small or distant, plays in perfect harmony. Quantum particles jitter at frequencies locked to the hum of gravitational waves. Pulsars flash in time with the expansion of space itself. Even our own circadian rhythms might subtly resonate with these universal beats. If true, this grand unification wouldn't just connect disparate phenomena, it would reveal time not as a backdrop to existence, but as the very fabric from which existence is woven. The hunt for this master clock takes physicists to the edges of known science. Some search for clues in the quantum realm, where entangled particles seem to share a hidden synchrony across vast distances. Others study black holes, where gravity's grip distorts time so severely that it might reveal how microscopic and cosmic clocks intertwine. Then there's dark matter, whose invisible bulk could be swaying to a rhythm that subtly guides the rotation of galaxies. Each of these threads, when pulled, leads to the same tantalizing question: are we seeing isolated mechanisms or the scattered pieces of a single, elegant timekeeping machine? One bold hypothesis suggests the answer lies in the vacuum of space itself. Quantum field theory describes empty space as a seething foam of virtual particles, constantly flickering in and out of existence. What if these fluctuations aren't random noise, but the ticks of a primordial clock, a foundational rhythm that all other timekeepers inherit? Experiments with ultra-precise atomic clocks have detected subtle anomalies that could hint at this deeper layer, as if the devices are occasionally nudged by an unseen hand synchronizing them to something greater. The implications ripple across disciplines. Biologists wonder if life evolved to exploit these universal rhythms, explaining why organisms from bacteria to whales exhibit internal clocks so finely tuned. Astronomers probe whether galactic collisions or dark energies push might leave detectable imprints in the timing of pulsars. Even philosophers grapple with what it means if time isn't just a measurement, but a dynamic, interconnected phenomenon, a conversation between every particle and force in the cosmos. Yet the grandest revelation might be this: if such a master clock exists, it wouldn't just unify physics. It would dissolve the artificial divide between the observer and the observed. Your perception of time passing, the steady tick of a wristwatch, the aging of stars, all would be threads in the same tapestry, each influencing the others in ways we're only beginning to glimpse. The universe's clocks aren't just keeping time, they're telling a story, one we're finally learning how to hear. From the vibrations of atoms to the spin of galaxies, the universe is a symphony of subtle clocks, each ticking in perfect harmony. But this isn't just a scientific curiosity, it's a profound reminder that we're embedded in something far grander than our daily routines. Every heartbeat, every sunrise, every moment you glance at your watch is part of an intricate dance stretching back to the first tick of the cosmos. These clocks aren't just out there, they're in you, in the air you breathe, in the light from your screen reaching your eyes at this very second. Think about what that means. The same quantum jitters that power atomic clocks also spark the neurons firing in your brain. The gravitational waves bending space-time around colliding black holes subtly tug at the tides and even the magma beneath your feet. Time isn't something that happens to the universe, it's how the universe happens, a rhythm so fundamental that without it, reality as we know it would dissolve into chaos. And yet, for all we've uncovered, these clocks still guard their deepest secrets. Why do quantum vibrations sync across vast distances? How does dark energy's acceleration tweak time's flow on cosmic scales? Could life itself be a kind of biological metronome, fine-tuned to the universe's hidden pulse? The beauty of these questions is that they're not just for physicists. They're for anyone who's ever stared at the night sky and wondered. Every time you check the clock, you're tapping into the same cosmic machinery that guides planets and particles alike. So the next time you feel rushed or impatient, remember, you're not just counting seconds, you're riding waves of time forged in the Big Bang, shaped by black holes and woven into the fabric of your existence. What's your take on these cosmic clocks? Have you ever felt connected to something bigger through time's mysteries? Drop your thoughts below. We're all part of this conversation, just as we're all part of the universe's timeless rhythm. And if you're hungry for more journeys into the unknown, hit that subscribe button. The cosmos has countless stories left to tell, and we're just getting started.